Hi everybody, and welcome back to Digital VLSI Design. I'm Professor Adam Teman of the EnICS Labs at Bar-Ilan University, and today we'll be going over the Kahoot for Lecture 7, Placement. So today's Kahoot will have 9 questions, and the first is, a 100 million gate ASIC really has about 100 million standard cells, 100 million instances, about 100 million NAND2 equivalent gates, or probably about 50 million instances. And actually, this is a pretty tough one, but I'll go with this yellow answer. So what is chip size? And before we started to discuss how to place the standard cells, we wanted to ask what it means when somebody says we have a 100 million gate ASIC. And this is just a kind of way of speaking to each other to, estimate sizes or complexity of the design. And when we say a 100 million gate ASIC, we're usually talking about the size of the chip, the size of the floor plan that we need. It's very interesting, though, if we were to look at a histogram of saying what the normalized width of cells are. We see that this study, an old study from IBM, but this is pretty much true today too. We see that most of the cells are really, really small. You see that they're only a small number of NAND2 equivalent gates. We only have really a few huge cells, which are probably hard macros like memories and so forth. So what we do actually is we usually take the entire size of the floor plan, or the total integral on all the sizes of the standard cells that we have, and we normalize them to NAND2 gates. So gates equals equivalent NAND2 gates, because NAND2 is really our workhorse of CMOS. It's our basic kind of a gate. We also saw that we kind of gave it, a small score or something like that in our technology mapping and so forth. So usually we talk about the equivalent NAND2 gates, and that means that one SRAM can be very, very many of these NAND2 gates, where one flip-flop will be several of these NAND2 gates, and a NAND2 will be one NAND2 gate. But there's another question, which is complexity of the algorithms that we're going to run, because when we discuss algorithms, we're talking about how long it will run on our machine and how complex it is to figure out. And then we really care about instances, because for example, for placement, we're going to want to place instances, so we care about the number of instances and not their actual size. And the instances, just as a rule of thumb, and this is an old rule of thumb, but I think it holds water today, it's the number of gates divided by about 4 or 5. So going back to our Kahoot over here, a 100 million gate ASIC really has about 100 million NAND2 equivalent gates, or at least that's the size. When I said probably about 50 million instances, that's only 100 million divided by 2. So we probably have less instances than that, something like 20 million instances. So question number 2. Half perimeter wire length, HBWL, is a cost metric defined as x1 minus x2 squared plus y1 minus y2 squared, delta x plus delta y, square root of delta x squared plus delta y squared, or 2 pi times delta x plus delta y. And I'm going to go for this one, which is pretty simple. So if we listen to the lecture, we saw that when we were designing our simple placer, we had to give some sort of cost metric, and cost metrics are really important. We have to have a way to measure how optimal we are, and we have to have some sort of a function that will that we are trying to optimize. And what we decided basically in placement, and this is kind of a decision that's takes in a lot of years of experience and some just estimations. We think that wire length is a good estimator to optimize. So we know that wire length is somehow proportional to the size of the chip. It's proportional to how far standard cells are away from each other. It's proportional to how slow we are, because we have to drive these long wires, how much power we are going to be wasting, because we have to charge and discharge the capacitance of these large wires. So wire load is kind of a good estimator that helps us optimize our placement. Is it the perfect thing? No, but I don't have a better answer for you today, so that's why we decided to take wire length. And how do we estimate wire length? We have to take some sort of a metric that is, number one, simple to calculate, easy to calculate, because we're going to have to calculate it many times. And second of all, that we're going to be able to optimize in terms of the math and so forth that goes with it. And really the easiest estimator we could think of is this half perimeter wire length. So what we're going to do is we're going to take our gates, which we're going to assume just are a single point on a grid, and we're going to cover them with a rectangle. Now this is good for a 2-point type of a net that just has a driver and a receiver, but it's also good for, you know, a net with high fan out. So here we have a driver and 3 receivers, and we actually don't care who the driver and the receiver is. We just need to know that this net is going to connect all of them. And what we do, if we put our rectangle around all of these points, then we can get a good estimation of what the size of the net is. Now, why is that important? Because, again, if we take 2 of these gates and we make them very far away from each other versus having 4 gates, which you would assume would have a longer wire, but we put them close together, the actual wire length of the large fan-out net is going to be much smaller. So this type of an estimator really helps us get some proportion of what the actual wire length of the net is. And half perimeter, well, the perimeter of this rectangle is just going to be, you know, the size of the x edge plus the size of the y edge times 2, right? 2 x edges and 2 y edges. The 2 is just a constant in our optimization, so there's no reason to multiply it by 2. So we just take half of the perimeter, and that's where we get half perimeter wire length. So, of course, our answer is going to be delta x plus delta y. Question number 3. What is the main problem with a simple random placer? Is it that randomization is never a good heuristic, that the runtime is really long, that HBWL is a bad metric, or that it easily gets stuck in local minimum? And actually, I'm going to go for the 4th answer here. So the question is randomization never a good heuristic? And no, I don't think that's true. We actually find out in many different algorithms, many different heuristics in across the entire spectrum of writing algorithm, that sometimes randomization actually works pretty well. And even in the case of the simple placer, randomization is not that bad. So I wouldn't say that randomization is never a good heuristic. The runtime is really long. Well, runtime is something that's kind of relative, and what is long and how much is the runtime? With our simple placer, we're going to stop it after a certain number of iterations or after we stop improving and so forth, and that may not take too long. Remember that each iteration is really simple. We're just going to swap 2 gates and then recalculate, you know, the half perimeter wire length based on the change from the previous wire length to the next one, which is a really simple calculation. So the runtime is not necessarily that long. Is HBWL a bad metric? No, actually, I think it's a pretty good metric, as I showed before. So the answer is that it easily gets stuck in local minima. And really, that is our kind of a problem that we have here. So let's look at our graph. And we tend to show this problem with minimization and optimization in kind of a 3-dimensional or maybe a 2-dimensional type of a space, because more than that, we can't visualize it. And if we have a ball here and we want to get to when we want to minimize it, depending on where our starting point is, we're just going to do this, what is called hill climbing, or in this case, because we're doing minimization, we're going to do descending. We're always going to go towards a better place, and we're going to get to some sort of a minimum, but that minimum, it may not be the global minimum. In fact, there's a very low probability that it's the global minimum. It'll just be a local minimum. Is that local minimum good? Well, it's better probably than where we started out. Assuming we didn't start out in the local minimum, we're always going to get a better answer. But next to the global minimum, it may be very, very poor, especially when we go and take a mini variable space, like a mini dimensional space. Really small changes, they're going to be mini local minima, and they're going to be very different from the global minima. And if we do hill climbing, if we just descend in where we take a good answer, we're probably going to go to just a random local minima that we found, and the most probability is it's going to be really bad. So that is a problem with hill climbing, with standard hill climbing, and that's why we have other methods such as simulated annealing that try to get rid of those just real easy local minima that depend only on the place that we started our heuristic. So, question number 4. Why is simulated annealing preferable to random placement? It randomly selects rather than hill climbing to get out of local minima. It's only a pseudo-random algorithm, which is better. It follows natural physical processes, which work, or it reaches a solution faster. And actually, these 3 are just kind of things that I made up. This is obviously the answer, as we mentioned before. So again, let's go back to the slide we just saw. And what we're going to do with regular hill climbing, or hill descending in this case, depending on where we started, we're gonna take some sort of a random change. We're gonna see where we get to. If it's better, we're gonna keep it. If not, we're gonna throw it away. So let's say we chose this dot, that's good. Then we chose that dot, that's not good. We chose this dot, we chose this dot, it's good. And we're going to keep on going until we really find the minimum of the local minimum of the area. And that's okay, again, but it gets stuck in that local minimum, which depends really on the place we started. With simulated annealing, what we're going to be able to do is every once in a while, we are going to take that jump backwards. Now, on a high dimensional domain, where we're going to have a space that has many variables, and not just these, 2 or 3 variables, depending on how you look at it over here in this visualization. Really, small steps in one direction or another are going to have sometimes a really high effect on how we get to what the local minimum is. So the idea of simulated annealing is that we'll usually go down, we'll usually do the hill climbing, but every once in a while, depending on some sort of probability, we'll randomly choose to take a bad solution. And that maybe will jump us over, to a different place and allow us to actually get to a farther local minimum. Now, this is not done constantly. What we're going to do is we're going to have this temperature variable, which means that the probability of taking a bad solution is going to be high at the beginning, and it's going to go down as we gradually advance in our iterations, assuming that we're going to find better and better local minima on the way, and we don't exactly want to throw them away until we get to this, really cold temperature where we're just going to do basically hill climbing, because the probability that we're going to take a bad solution is very low. Well, how well does this work? And we see, if we started over here, we're going to want to be minimizing our wire length. And really, every time we go up in this, it means we took a bad solution, which is some sort of, again, a probability that we're going to actually jump in the wrong direction. So we took a bad solution, but in the end, we're going to really keep on going down until we find a really good solution. And that's pretty cool. If we look at this, we get to this nice S-curve, which gets us to a really good solution. Simulated annealing is an important algorithmic concept. It's not actually what we use in placers today. We are going to use more analytical placement. But we'll use simulated annealing in some parts of the algorithm and in other parts of our physical design. Question number 9, why do we use quadratic wire length rather than HBWL for analytic placement? Well, is it because it's easier to calculate? Is it because it's more accurate? Is it because it can deal with K-point nets? Or is it just because the math works better? Well, actually, it's just because the math works better. So, oddly, if we look at quadratic placement, or at our quadratic wire length, what it is we're going to actually measure the distance, or at least the distance squared, between 2 points. So we take x1 minus x2 squared plus y1 minus y2 squared, and if we were to take the square root of that, we would get the length of this line over here, the distance between these 2 points. Now, is that good? Is it easy to calculate? And the answer is it's not very hard to calculate, but probably this is harder to calculate than just the half perimeter wire length. So I don't think that's the answer. Now, this is only good for measuring, again, the distance between 2 points. What happens when we have a third point? And for the third point, what we're going to do is we're going to actually break our whole net, our multi-point net, into a clique model. So we're going to make these connections, these point-to-point connections, between every pair of gates we have here. And then we can find the distance between all of them and sum them up. The thing is that the sum of a large fan-out net will usually be higher than the sum of a small fan-out net. So we're going to have to normalize or reduce the weight or the effect of each one of these extra connections that we added. And we could do it by dividing by, k, by the number of gates we have here or something else. We decided to do it by dividing by k minus 1. And that is a way to reduce the weight of each net, but still give some, weight to the fact that we have a high fan-out net versus a small fan-out net, which will usually increase our wire length, at least in a similar type of an area, because we're going to have to connect to all of the gates there. So going back to you know, the Kahoot answer, is it easier to calculate? The answer is no. Okay, and it can deal with k-point nets, yes, but HBWL obviously can deal with k-point nets. Okay, is it more accurate? No, it's just a different way to estimate our wire length. We don't know which one is more accurate. We could do a study on it, and I'm sure there have been many, but I can't say out of the box that it's more accurate. But the reason we do it is because the math works better. As we saw, and we're going to discuss now, in analytical wire length, we just, you know, get some sort of a cost function that we can then, you know, put a derivative on and minimize and find the optimal minimum point. And that we can do because of this, the design of the cost metric, you know, the cost function, the metric, the quadratic wire length, which allows us to actually do that type of derivative on it, which we could do easily, at least with HBWL. Question number 6. Why doesn't quadratic placement provide a realistic optimal solution? It's because it's too hard to solve such large matrices, because it requires all gates to be the same size, because it tends to cluster too many gates in the same area, or because it gives too much weight to the pin locations. Well, I think that the answer is because it tends to cluster too many gates in the same area. So again, let's go back to our analytical placement, and what we see is that we're always going to get a solution from analytical placement that looks something like this. In fact, the way to reduce our wire length is to just put all the gates in the same exact place, and then the wire length between them is going to be 0. The reason that we do have some sort of spread is because of our anchors, because of our pins or ports, depending on what you want to call them, that are around the periphery, and they are pulling some of the gates that are, you know, that are talking to them, that are connected to them, towards the sides. And that's what's going to scatter it a little bit. But in the end, we're going to have this big mess of these single point, you know, dimensionless gates that are going to be really in the same place. And obviously, that doesn't work. We can't put all of them there. Once we start going and bringing in our physical information from our left into the design, we're going to have a ton of overlap. So what we need to do is scatter it. There's another point here that we actually have a floor plan that is not empty. It's not one empty space. We said we want to have, you know, a floor plan that leaves these empty spaces inside, and it's just exactly because of this thing that we want to be able to put the gates as close as possible to each other. But we're going to have macros scattered all around, and you see that there are over 500 IPs in just this chip we see here, and obviously we cannot put gates on top of them. And another thing, it's going to be hard to route and stuff around these macros. So we need to really scatter things, and the way we're going to scatter it is through recursive partitioning. So the problem really with the quadratic wire length is that it clusters. Okay, so it's not hard to solve such large matrices. I mean, it is hard, but we have good computing power and we have good ways to solve these matrices, and it's something that we can deal with. Because it requires all the gates to be the same size, it does not require the gates to be the same size. It assumes that all the gates are dimensionless, but then in a later stage, it's going to add the actual physical parameters and fix all the overlaps. So it doesn't require anything to be the same size. It just assumes that they are in order to solve the equation. Because it gives too much weight to the pin locations. No, the weight of the pin locations is set by the algorithm, and if it was giving too much weight to the pin locations, we would reduce their weight, but that's not the problem. The problem is because it tends to cluster too many gates in the same area. Question number 7. Why do we need placement legalization? Because the government hasn't passed a law yet, I think it's that one, right? To remove overlaps and move gates onto the placement grid, because simulated annealing provides good results to move the pseudo pins to real locations. And I think this one's pretty straightforward. It's to remove overlaps and move the gates onto the placement grid. So again, let's go back to our slides over here. And when we discuss legalization, this is really important. So again, we did this recursive partitioning, and in the end, we got a nicely scattered, you know, solution of the gates all over the place. But the gates are still dimensionless. We still may have, you know, 2 gates that are sitting on top of each other, really close to each other within a certain partition. And we also have our macros and so forth that are going to be bothering us. So what we need to do actually is snap back our gates into place. So think of it as like a piece of a Lego. You know, we want to put this Lego on top of the other. We have to play around with it until they snap together. And the same thing here with our gates. If our gate was, you know, once we take our point and we add our dimensions from our left, you know, we're going to have a gate sitting somewhere, and we need to put it onto the standard cell row. And then we're going to have a bunch of gates that are overlapping with each other. So we need to move them. And how do we move them? Well, we should use some sort of heuristic, such as simulation simulated annealing. So simulated annealing will work well for legalization, you know, to randomly swap until we get a pretty good solution when we have a better, you know, wire length type of an estimator. But it's not going to, you know, provide an optimal solution. It's just a way that we're going to solve the problem of overlap and the problem of legalization of the cells, of where they can sit inside the rows without, you know, losing our optimality of our solution that's before. So we're going to still get a good solution without, you know, just randomly taking this gate and throwing it way over there because there was an open space. We're going to move it somewhere that's not going to hurt our HBWL that much. Okay, so really, if we said because simulated annealing provides a good results, that may be true, but that's not the reason that we need placement legalization. That may be a means to carry it out. To move the pseudopins back to real locations, the pseudopins are just a virtual thing, you know, that we use for our recursive partitioning. They basically disappear once we finish our recursion over there. So that has nothing to do with anything. To remove overlaps and move the gates onto the placement grid is the right answer. Question 8. How do we estimate RCs to achieve timing-driven placement? By using wire load models, based on the quadratic wire length of the net, using virtual routes or trial routes during placement iteration, applying DRC clean detailed route following placement. So the thing is that we're going to use virtual routes, or also known as trial routes, during placement iterations. And let's go back to this one too. So timing-driven placement. So everything we talked about was optimization of the wire length. Wire length is really nice, but everything we talked about in our previous lecture on static timing analysis was that we're trying to meet constraints, that the main constraint is timing. And how does wire length relate to timing? Well, we think it is proportional, and that's why we use wire length as a metric. I mean, because of timing, because of area, and so forth. But it is not correlated one-to-one. It doesn't take into account anything like critical nets and so forth and so on. So we want to really have some sort of optimization of timing within our placement algorithm, and it's tough. Once we have, you know, more than one cost function, how are we going to deal with it? And actually, with placement, we have several cost metrics, several objectives. We want to have, you know, the smallest area possible. We want to meet timing. We want to be able to route, so we want to reduce congestion. We want to have good power in the end. And these are all, you know, things that we could maybe optimize separately, but it's hard to optimize them together. And we decide to go for wire length as the thing we want to optimize. But within that, we want to also improve timing and look at timing and take timing into consideration, so we can really try to heuristically focus on how to improve the timing of certain nets, you know, and certain paths that are going to be critical in the end. And to do that, we could use a wire load model such as we did in synthesis, but we said that wire load model is a really, really bad estimation. It just takes the fan out of a certain gate and estimates what the RCs are in order to put them into the timing model. And that's really bad. Now we have the benefit of the fact that we actually know the location of the cells because we just did placement, or we're in the middle of placement. And therefore, we know what the real distance and how things have to get to each other. So what we can do is we can do routing. But routing is a tough, long process, as we'll see in one of the following lectures. And so we're not going to go and do what we call detailed routing, where we go and fix, you know, DRCs and so forth and so on. So what we're going to do is we're going to do just this kind of a virtual route or a trial route. We're going to do a quick and sloppy route. We're not going to fix any DRCs, not going to fix any shorts and any opens and so forth. We're just going to go and see if we took a wire that has to go, you know, to another cell, how it's going to go over there, and do it real quick and sloppy with one metal or something like that. And then we're going to extract the RC of it to get a good estimation. It's going to be in the ballpark of the real RC of the wire, but it's not going to be by any means accurate. We do this for the speed and for getting much closer to the estimated RC, and not to get an actual RC, which we'll only be able to do after we have a full detailed route. So using wire load models is not the way to do it. We said that wire load models are really bad. They're real ugly. They're just kind of good for real old synthesis. What we want to do is really have good estimation. Based on the quadratic wire length, and the quadratic wire length is a nice thing. You know, it gives us some sort of estimation, some sort of ballpark or order of magnitude of what our wire length is, but it's just an estimator used for optimization. It's not something for actually measuring what the RC of a net is. Applying DRC clean detailed route following placement, well, as we said, that's going to be too time consuming, too hard to do at this stage, so we're going to do it later on. What about using virtual routes during placement iteration? So we said that's kind of the best of both worlds. It's quick, it's a bit dirty, but it's quick, and it gives us a good ballpark estimation of what the RCs are. And finally, for our last question today, what is overflow? In the context of place and route, of course. We're not talking about overflow in general when, our bath overflows because we forgot to turn off the faucet. Pin density higher than 50% in a certain global bin. Routing demand minus routing supply if bigger than 0 at a certain edge. More horizontal tracks than vertical tracks in a given area. More than 35 nets crossing a global routing cell at a given edge. Well, I think it's actually going to be the blue one. I happen to miss it over here, but let's go back into the slides and see what it is. So congestion. Congestion is the situation where, similar to cars driving on, routes in a busy area, we have more cars than we do have, lanes and so forth to have the cars drive on them. We're going to get traffic. And that's the same thing with wiring. We're going to have wires that are going to want to go from one place to another, but we don't have enough space to route them. We don't have enough routing tracks. So the routing tracks are the number, basically, of wires that we're going to be able to route in a certain direction in a certain area. Okay, and the number of tracks is simple. It's actually defined in the teclef, and it's basically the minimum space and minimum width of a wire. That is the size of one track. So we take the width of a certain area, divide it by this track size, this minimum width plus minimum space, and we get the number of routing tracks in that metal layer. And then we can go up to all the metal layers. Usually going to be if we have a vertical metal layer here of metal 2, then it's going to be metal 2 plus metal 4 plus metal 6. Of course, the number of tracks changes by the size in the DRCs of that metal layer, but that is the total number of tracks that we have available to route in a certain area. The demand is when we do our trial route, we're going to see, or a trial route, or just by looking at the placement that we have right now, it's going to show us how many tracks we actually need in that area, because we need to go from a standard cell that's sitting over here to connect to one that's sitting over here. We know we're going to need a wire that's going to go through this edge. So we look at each edge, both vertical and horizontal, say how many tracks we have available on that edge. That's the routing supply, basically. And we ask how many routes we need to go and cross that edge. That's the routing demand. Okay, and if the demand is larger than the supply, we're in trouble. That is called, overflow. So overflow means that we have more wires that need to cross a certain edge, divided by the number of wires that that are possible to go over there by full capacity of the tracks. Otherwise, we don't have overflow, so it's 0. And the total overflow of the design is taking all of these global bins that we divided our design into, measuring all of the edges of the global bins, seeing what the overflow for each of them is, and summing them up. That's going to be the total overflow. In general, we can live with overflow. Small overflow, such as this, we have 29, demand and 28 available. That's something we can live with. We can always route around. But if we have lots of overflow in a certain area, we're not going to be able to route the design. We're going to have to go back to the floor plan, try to fix things in the floor plan, move things around, maybe put some partial placement blockage to reduce the utilization in that area, etc. So going back to our Kahoot, pin density higher than 50% in a certain global bin. Well, I mentioned in one of the lectures, I'm sure, that pin density is something that can cause overflow. So if we have, something like a multiplexer, 4 input multiplexer, we're going to have 4 inputs, 2 selector inputs, and an output. That's 7 pins on a standard cell area. Versus if we take, a really big inverter that's going to be really wide, but it just has an in and an out, there's very few pins. We have to connect very few nets to that cell. So pin density is something we don't want, but saying pin density is higher than 50% is just kind of waving our hands. We want a real metric that can show us what overflow is. So maybe pin density higher than 50%, and I'm not sure what that 50% even means. It was just something I made up in a certain area, may cause overflow or may cause congestion, but that sure is not the metric. Okay, the definition is routing demand minus routing supply. If it's bigger than 0 at a certain edge, that's the definition of overflow for that edge. More horizontal tracks than vertical tracks in a given area. That is not something that causes overflow. It may be something that's not great. It's something that maybe we could live with. More than 35 nets crossing a global routing cell at a given edge. Well, if we have 35 tracks, then yes, then this would be overflow. But who said we have 35 tracks? So that's not the right answer either. So that was it for our Kahoot for this time. And if you have any questions, as always, you are invited to ask me about it on my YouTube channel. Did I get first place? I did. Great.